Hi, this video is a quick getting started guide for using the Concurrent programming language. We're going to start off by using the Concurrent REPL environment in order to look at some of the features of the language, and then we're going to be using the command line compiler and runtime in order to run some programs. So let's get started. For the purposes of this video, we're going to assume that you've already installed Concurrent and added it to your path. In order to start the Concurrent REPL, we used a conc command line tool. Let's begin by creating a variable, a equals 10. Concurrent is a type-inferred language, hence a has been inferred to be of type integer. If we want to be explicit about the type, we're allowed to do that as well. Here we've created a2 and been explicit about the type. We may optionally use val and var when we're creating new variables. For example, var b equals 10, val c equals 9. Using val prevents reassignment to the variable. You see here, when we attempted to reassign a value to c which has been declared as val, it gets flagged up as an error. So far we've seen scalar variables, but we can also create arrays as follows. Lists are also easy to create, as well as matrices. Concurrent has first-class citizen support for tuples. Here we've created a tuple of size 2, and we can dereference tuples as follows. Now let's have a look at some operations that we can perform upon variables. Concurrent has support for the usual suite of numerical and equality-related operators. Let's first define a variable. Now let's do a plus a, and let's have a look at some other examples. 10 is greater than 4. 3 is less than or equal to 8. And a is not equal to 20. Concurrent has first-class citizen support for a technique known as vectorization. First we define an array. We can perform a vectorized add as follows. Here we see that 10 has been added to each element of the array, but the data in the original array remains unchanged. We can perform an in-place vectorized operation as follows. Now the original array is also updated. Let's now have a look at blocks and control structures. In Concurrent, all blocks are capable of returning values. For example, this is an incredibly useful feature, especially when we're working with branching logic. This helps us to write very concise algorithms which would otherwise consume many lines of code in a traditional programming language. Though in the case of the previous line of code, we're able to use an if-else expression. Looping structures also return values. Here we define a for loop which adds 10 to each element of an array, though for this case Concurrent also supports list comprehension. The fact that all blocks are able to return values makes for some very concise function definitions, as we shall see later on. Concurrent runs on the JVM. Therefore, we have access to the JDK, which provides excellent implementations of common data structures such as lists, maps and sets. Let's create an array list. First we need to import it. Now let's create an instance of an array list. Concurrent has first-class citizen support for sets, lists and maps. Let's create a set. S is of type hashset with generic qualification of integer. Notice how we didn't define the generic type qualification. This is because Concurrent has a special feature known as generic type inference. Let's now create a list. Because lists are such a useful data structure, Concurrent has special first-class citizen support for them, as we've already seen. In fact, this is a really useful way of defining sets. We can create maps as follows. There's also first-class citizen support for operations on common data structures, such as list indexing, and checking to see if a value is in a set or a map. We can get and set values from maps as follows, and also remove key pair mappings. Let's now have a look at how we can use functions in Concurrent. Let's define a factorial function. Notice above we're using the match structure. This is an incredibly useful piece of syntax, which can be used to write code, which would otherwise require a large if-else block. Let's now make use of our factorial function. Notice also above we're using list comprehension and also a range expression from -1 to 10. For simple functions, Concurrent allows you to use a very concise syntax. Above we define the body of a function in one line and also infer the return type. Let us now look at a bit of functional programming. Let's define a function reference. Do plus is now a function taking two integers and returning another one. We can also define this function reference in a more concise manner as follows. We can also qualify function parameters when making function references. Add one above is now a function reference taking an integer and returning another one. Concurrent has first-class citizen support for anonymous lambdas. Let's define a map function now which makes use of a lambda. And now let's define a lambda to pass to our map function, which will multiply each element of the list by 10. Let's now have a look at support for object-oriented programming. First, let's define a data-oriented class. Now let's create two instances of this class. Concurrent will automatically define an equality and hashcode function for all classes, thus making the following code possible. Note that this isn't a trick. The two person instances are indeed different objects. Getters and setters have become synonymous with modern object-oriented programming in order to support encapsulation, but they're not fun to define. Luckily, Concurrent takes the hard work out of this. Here, our gettable class defines two fields, A and B. The dash before A informs Concurrent that we wish to generate a getter function for A. The tide before B indicates to Concurrent that we wish to generate both setters and getters for B. Let's now create an instance of this class. And we can call our automatically generated getter function. Concurrent also possesses smart mapping to getter functions, thus the following code is perfectly valid and equivalent to the previous line. We can call a setter function as follows. And assignment is automatically mapped to this setter too. There are a lot more interesting aspects to the support for object-oriented programming built into Concurrent, such as traits, subclassing and abstract classes, but we don't have time in this video to cover all of them. Concurrent is a null-safe language. That is to say, nullability of an object is part of the type system of the language itself. By default, all objects are assumed to be non-nullable unless otherwise defined. In traditional programming languages, any object may become null at any point in its existence. For this reason, when writing safe code, we must perpetually check for null. Most developers skip this process, and hence the null pointer exception is one of the most common thrown. Concurrent solves this problem by including nullability as part of its type system. This helps us to write much safer, cleaner code. Let's start by defining an ordinary non-null variable. Concurrent does not permit us to set null to this variable. If we want the option to set a variable to null, we can define it as follows. Now our variable can take a null value. The same applies to function invocations. Our function here cannot receive a nullable parameter. In order to pass it null, we must adjust the input variable as appropriate. Notice how Concurrent complains when we do this, as it may invalidate the length call. There are a number of ways we can mitigate this unsafe operation. One of them is as follows. By using the double question mark, we tell Concurrent that if the variable a is null, it should throw a null pointer exception. And indeed, this is what happens. Another strategy is as follows. Here, Concurrent will return null and not invoke the length call if a is null, thus avoiding a null pointer exception. Finally, Concurrent offers what's known as the Elvis operator, in order to avoid both a null pointer exception or a null value being returned. Oops. The functionality in Concurrent we've seen so far can be best described as classical programming. Now let's look at what makes Concurrent unique, its concurrency model. We'll start by defining an ordinary function to calculate the greatest common divisor of two integers. We will now create an isolate. An isolate is a block of code which operates within its own concurrent thread of execution. If an isolate returns a value, that value is of type ref. The bang operator indicates that we wish a block of code to be executed as an isolate. The bang operator can also be applied to individual function invocations to tell Concurrent that we wish that invocation to be executed as an isolate. Above, we explicitly state the return type of the isolate, being a ref of type int. Isolates, when being executed, get multiplexed onto the underlying hardware of the machine that they are operating on, so you can spawn many thousands of isolates. The only limiting factor is the amount of memory available on the machine upon which the code is being executed. This is quite a different model from thread-based models of concurrency, and it's much easier to understand and program. Refs are essentially variables which can be shared and modified by multiple different isolates in a controlled, concurrent manner. Our two isolates that we have previously spawned are now running concurrently. Let's now define an expression which uses the values of calc 1 and 2. Calc 3 can only be calculated when calc 1 and 2 are available, and these two values are only available when the two spawned isolates have completed their concurrent execution. Together, isolates and refs help support reactive programming. Let's look at an example of this now. First, let's define a ref. Now let's define an onChange block. OnChange blocks operate within their own dedicated isolate. Whenever an input ref to an onChange block is changed, the onChange block's body is triggered for execution. Let's look at this now. Concurrent also offers a compacted form of this syntax. Let's define two refs now. And now let's create our compacted onChange block. Here, whenever A or B are changed, the value of the ref C is updated. Let's now add an onChange block to monitor C for any changes itself. So you can see here how we've effectively created a reactive graph for ourselves. Let's see what happens when we change the value of b. C is updated and the value printed out. Concurrent offers three aspects of support for domain-specific languages, or DSLs for short. This is in the form of operator overloading, extension functions, and expression lists. Let's have a look at them now. We'll start with operator overloading. Let's take a classic example of a complex number consisting of a real and imaginary component. Let's start to define our complex class. Now let's make use of operator overloading in order to add plus functionality and in-place plus functionality to the complex class. Let's now create a complex object and make a deep copy of it using the ampersand operator. Now let's add the two together. Neat. All the standard operators in Concurrent can be overloaded via this mechanism. Now let's look at extension functions. Extension functions allow for functionality to be added to classes without needing to interact with the class hierarchy, i.e. extending the class, etc. They are a convenient alternative to having to use utility functions, methods, or classes which take an instance of a class and often permit a more natural way of interacting with objects. Extension functions may be defined on any type, including primitive types. Let's define a repeat extension function operating on the string type. And we can use it as follows. Now let's look at expression lists. This is a neat feature which enables a more natural way of writing expression-related code that would otherwise have to be written as a set of chain-together calls using the dot operator and or function invocation brackets. Let's take a simple multiply function. Using expression lists, we're able to call the multiply function as follows. Now let's throw a class into the mix. And let's define an even more complex expression list. Expression lists may be combined with operator overloading and extension functions to achieve some very impressive results. For example, let's define a plus extension function operating on the type integer. The following is perfectly valid code. Now, let's start using the Concurrent command line tool. Here, we have created a conc file, which is essentially a glorified hello world. We have a log, utility function, a sayHello class, and a main method to drive execution. Let's now compile this code. To do this, we can use the conc tool. And we can use conc in order to execute this code. We can generate a jar for our hello world as follows. Notice here that we define the entry point as hello. This enables the following form of execution using conc. Concurrent has first-class citizen support for GPU computing. Let's look at a quick example of GPU computing now. Here we define two utility functions. Next is our GPU kernel. Note that this code is idiomatic Concurrent code, fully syntax and semantic checked at compile time. Next is our main method. This method sets up our GPU, creates a matrix to copy into the GPU, initializes the GPU kernel operation, performs some cleanup, and then prints the result. Let's see this in action. First we need to compile it. and then we can run the code. Finally, let's look at temporal computing, another aspect of reactive computing enabled by Concurrent's unique concurrency model. The essential idea here is to create a ref which is updated every second 5 times. We then react to changes in that ref and print out the current time. So let's see this in action. First we compile the code. And now we must run conc in server mode, such that Concurrent won't shut down after completion of the main method. Great. And this now concludes our Getting Started guide.